inlet velocity needs to be adjustable as well. Bottom drain outlets, you really need to think about the fish exclusion screen and the approach velocity of the water through there. So it's really important to think about the flow and the approach velocity. Collection sump underneath needs to be designed so that it doesn't collect solids as well. And the discharge pipe velocity needs to maintain those solids and push them through the system. Side drain outlets, also fish exclusion and velocity. There's also some water level control that can take place in the side drain outlet, and it can be also used for fish management and water collection. So the operational goals for all of these are to improve fish welfare, more efficient oxygen uptake, the appropriate velocity for trout is really important, so that you push the water and the oxygen across their gills, and they don't have to pump the water across their gills, and they're not fighting a current that's too heavy for them as well. So you have to really hit a sweet spot for salmonids and trout. Provide a well-mixed environment, so no dead zones, no oxygen depletion zones, or solids buildup. You remove the solids quickly from the tank. We're trying to get any uneaten feed or feces out of that tank quickly within 3 to 6 minutes. Allow for adjustability of those flow rates and the rotational velocity. And in general, trying to reduce the stress on the fish. So maintain saturated oxygen levels, low TSS, and good turnover rates to manage ammonia and carbon dioxide buildup. That's clear. So I really like this graph. This graph was done by Sommerfeld in 2006 at the Freshwater Institute. It represents a tank with a radius of about 4 meters. This is the center of the tank here in the center of the graph, and this is the sidewall of the tanks. He has a hydraulic loading rate of about 33 minutes, which is about 2 turnovers an hour, and an inlet nozzle velocity of 341 centimeters per second. The variable in this research study was the percent of flow through the center drain here. So he took a portion of the inlet flow and removed it through that center drain and determined how that impacted the velocity throughout the cross-sectional area of that tank. And what you see here on this one here, this is the 100% water exiting the center drain, and you see a velocity that just sort of goes off the chart here. That represents a vortex in the middle of the tank. So everybody's seen, that circular vortex, that tornado that gets created if you have too much flow and too much rotational velocity in the middle of the tank. So that's an indication that maybe you have a little too much flow going through your center drain. Drops down to 40% here, so you still see quite a bit of an increase in flow rate at the center, and then it drops off. You're not quite creating that vortex all the way up to the surface, but still some additional velocity in the center. And then at 15% center drain flow, it drops down into this area here. And what we're really trying to do is maintain sort of a constant flow across that whole tank cross-sectional area to give those fish a good consistent environment to live within. So really somewhere between that 15% and that 40% is where we probably want to be with the percent of flow through the center drain. However, sorry about the small text again. Center drain flow in percentage doesn't necessarily relate to different tank diameters and tank depths and things like that when it comes to turnover rates. So we've applied, sorry, I forgot one part here. So the water velocity near the tank walls is really controlled by the nozzle orientation and the nozzle velocity and the tank flow. The water velocity near the center drain is controlled by the surface loading rate on the center drain itself. That surface loading rate is defined by the flow per cross-sectional area or area of the bottom of the tank. So if you have a tank that has a certain number of square feet on the area, you apply a flow rate to that, and that's the surface loading rate. So surface loading rates are identified over here in liters per square meter. liters per minute per square meter and gallons per minute per square foot of bottom area. And what the research showed was that with lower turnover rates, so this is a turnover rate of 1, 2, 3, 4, lower turnover rates require a higher surface loading rate on that center drain. So I sort of modeled 4 different tank sizes, 10-foot diameter, 20, 30, and 40-foot diameter tanks with slightly different diameter depth ratios to sort of model what the percentage of flow looks like through that center drain in those different tanks. And what you see is that with a low turnover rate, this is 1, 2, 3, 4, at 1 turnover rate per hour, the small tank really requires about 100% of the flow to go through that center drain to achieve the appropriate surface loading rate that we're targeting for those tanks. As the tanks get larger, the surface loading rate creates less of a percentage through the center drain, and as the turnover rates increase on the tank, then you start to get down around this 20% down here. So you recall the last one we were shooting for 15 to 40%. So this area down here is where we really try and get to. Honestly. This just shows the actual flow rates associated with the center drain in this scenario here. So the next few slides demonstrate how we can sort of apply this technology to different applications in aquaculture. And the first one is really a single pass scenario, so a flow through system. And most people are used to flow through systems being associated with conservation aquaculture and raceways and things like that. But you can also apply it to circular tanks as well. But with a lower exchange rate, that 1 turnover per hour for flow through, you really require quite a high percentage of the flow rate to go through that center drain. So you have to be careful of vortexing and things like that in those scenarios sometimes. But this is achievable on these systems with the lower flow rates. I never design a system for 100% flow through the center drain. I always allow for some overflow or surface skimming off of the side. And I'll often design a side box for 100% of the flow in the event that a center drain does get clogged for some reasons, and you do have the opportunity to have an emergency overflow that contains the water to a fixed discharge location. So a little bit of flow for surface skimming, so you don't want all your flow through the bottom. You do want to, that would trap all of those oils and things that might collect on the surface of the tank. And you do want those to have an avenue to escape the tank and get to your treatment system or to the discharge. In a PRAS system, again, the reuse rate is related to the amount of recirculated flow. So here you see we have new water coming in from a surface source or potentially from a groundwater source. But 30% new water, 70% recirculated flow. So that's a reuse rate of about 30. In this scenario, the dual drain technology works quite nicely because what I would normally do is I would design the center drain flow to achieve as close as possible to this influent flow here, the new water coming in. Because we want to discharge this water here out of the system and not recirculate it. This center drain is where all the solids are going to collect, all the uneaten feed and things like that. So we want to get that out of the system and get it discharged to our effluent treatment system quickly. And then 75% would be recirculated and managed for gas exchange on this system. So you don't have to balance this percentage with this percentage and that one with that one, but they do tend to be relatively close. What I try and do is do slightly less percentage here than here, and then it allows for the remainder of the flow to be discharged either through solids removal or through an overflow on the sump. And with a RAS system, we've added some complexity. Now